All right. Um, I just wanted to do a little bit of an introduction into 12.5 for the binomial theorem. We're going to use what's called Pascal's triangle, and you may have seen this before. This is from the mathematician Blaise Pascal, who actually contributed a lot to the world of mathematics. And you're going to see just a tip of the iceberg fun facts about Pascal's triangle. All right. So notice at the top, yep, the mouse works here. It starts with 1, okay, and then 1 and 1, all right. And then to get the next rows, all right, you're going to see that um, you can add the two numbers above it. So 4 plus 1 here is 5. So that's where the 5 comes in. All right. Over here, this number is going to be 4 because of 1 and 3 right above. All right. And so you get this whole triangle. Okay. And so, right, look, 4 plus 6 is 10. 4 plus 6 is 10. All right. And so I always tell my students every year that they don't have to memorize the triangle because you can just simply make it by adding the two numbers above it. All right. The very first number up here, this is considered row 0. Okay. This is going to be important. You'll see why in a second. This is row 0, and then row 1, and then 2, 3, 4, etc., etc. Okay. All right. The first kind of neat thing about Pascal's triangle is called a hockey stick. All right. I'm going to start with this red one here. So if you add the diagonals here, 1 plus 6 plus 21 plus 56 equals 84. Right? Over here to the blue, 1 plus 12 is 13. Over here, if you add all of these diagonals here in the green one, 1 plus 7 plus 28, etc., all the way down here equals 1716. Okay? If you want to pause here and see if this works out, pick any diagonal, right? And then wherever you stop, it's going to equal the number to the diagonal below. So like, let's look at this one. 1 plus 2, 1, 2, 3, 4, 5. Does that equal 15? So 1 plus 2 is 3. 3 plus 3 is 6. 6 plus 4 is 10. 10 plus 5 is 15. All right, so you can choose any diagonal and that'll work out. And again, if you want, pause it and, pick another diagonal. All right, so that's the hockey stick. This one, I believe, is if you add the numbers in the Pascal's triangle horizontally, right? These are the sums, right? That's 1, 1 plus 1 is 2, 1 plus 2 plus 1 is 4. This next one is going to be 8. This next one is 16. And if you look at these results, right? Look at these numbers themselves. They're multiplying up by 2 each time. So the next one here is going to be 32, 64, and so on, right? And what you notice is these are all powers of 2, right? And look, these exponents are the row numbers. That's why this first one is row 0. It's to the 0 power, right? 2 to the 0 power is 1. First row, second row, third row, fourth row, and so on, right? It's pretty neat. The rubber band. I'm not sure why it's called a rubber band. So here, if you look at 1 and 3, right? 1 plus 3 is 4, and that's 2 squared, okay? Over here, 3 plus 6 is 9, which is 3 squared. All right, 6 plus 10 is 16, which is 4 squared, and so on, right? 10 plus 15 is 25, which is 5 squared. You get 36, 6 squared, that's 49, 64, what's next? 81, right? And then 100, right? That's 10 squared, okay? So you have these pairs diagonally of perfect squares. This is really, really neat. Powers of 11, all right? Right here, 11 to the, again, 0 power, right, is 1, okay? 11 to the first power is 11, and look, 11 is 1 and 1, right? 1, 1. Because look at 11 squared, that's 121, 121, right? 11 cubed is 1331, 1331, right? So the row of Pascal's triangle are the powers of 11, right? Now what happens here though? Because we have 1, 5, 10, 10, 5, 1, so what happens is these kind of collapse, if you will, into 1, all right? I'm gonna skip this part. The second diagonal, okay, if you look, it's just, these are what's called the natural numbers. These are counting numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, it's going to keep going, right? So the second diagonal shows the natural numbers. And I think before even Pascal had come up with this, all right, you can Google it, when Pascal had discovered this triangle. The Chinese had actually known about it way before, and they knew about this number system. Okay, we're actually gonna, and this is kind of the lesson on Friday, what we're gonna get into, binomial expansion. All right, we're gonna look at like what do we do when we have x plus 1 to the 6th power, right? Now this is what it means, right? We multiply all of that, okay? Okay, so, well, you know, I'm not gonna have you sit there and work this all out, but if you look at these coefficients, right? Right, 1x squared and then 2 and 1, 1, 3, 3, 1. Okay, 1, 4, 6, 4, 1. So these coefficients actually come from Pascal's triangle. Okay. All right. We're actually going to use this also for some combination stuff, which you guys learned about on Tuesday. I'll expand more on that in another video. Okay. All right. So this last bit is kind of neat. So this is if you were to add the sums of the diagonals, right? So 1, that's just 1. We have another 1, and then this 1 plus this 1 is 2, right? Then you have 2 plus 1, that's 3. 1 plus 3 plus 1, that's 5. And so what ends up happening is these numbers, and some of you might recognize this, is what's called the Fibonacci sequence, right? The Fibonacci sequence is you get the next number by adding the previous two. Okay, so you start with 1 and 1, all right? And 2 comes from 1 plus 1. 3 comes from 1 plus 2. 5 comes from 2 plus 3, and so on and so on. All right? So Fibonacci sequence is actually in Pascal's triangle. All right? I forgot what this some of the this was made like years ago, and so something with flower petals. There's Fibonacci sequence in there. I believe this is in the middle of a sunflower. All right, the pattern is Fibonacci sequence. I think in an acorn as well. Okay. It is not, and we're going to do some of this stuff in chapter 12. It is not an arithmetic sequence. Okay, arithmetic sequence means you add by the same number each time, but clearly it's not because I already said we're adding the previous two numbers. Okay, it's not geometric. Geometric means you would be multiplying by the same number each time. Okay, but take a look at what happens here. All right, when you do 1 divided by 1, 2 divided by 1, 3 divided by 2, 5 divided by 3, and what ends up happening is it approaches and gets closer to this number represented by the Greek letter phi. Okay, and it approaches this 1.618. Okay, it never gets there. It's kind of like an asymptote, right? It's getting closer to this value, but it actually never gets there. It's an irrational number, and this is what's called the golden ratio. This value of 1.618. All right, and the golden ratio actually exists everywhere. Right. This is Notre Dame, I believe. And when you look at the dimensions, okay, the white to the blue, all right, is a ratio of 1.618. All right, even vertically. Okay, I'm going to talk about that in a second. This is the famous painting of the Last Supper. Right, a lot of golden ratio in this painting. The pyramids. Okay, golden ratio here. The Parthenon in Greece, right? There's a lot of dimensions with golden ratio. Okay, I'm not really a music person. Some of you that are more inclined to music, you might know what this stuff means, the tritone and the diminished fifth. But there's golden ratio in music as well. Okay, a credit card, all right, is very close to a golden ratio. All right. If I were to ask you to draw a rectangle, all right, on a piece of paper and measure it, the length and the width, it would be, my guess is close to a golden ratio value, right? Because there's something, the whole point is there's something aesthetically beautiful about this number, right? When you draw something just kind of naturally, quote unquote naturally, it gets close to this ratio, all right? In DNA, all right? So much so that the Greeks, and this might be a little bit messed up, believed in the golden ratio to determine beauty, all right? If A is the length from the top of the head to the chin, and G is the width of the head, right? And so, you know, if you got close to that golden ratio, you were considered quote unquote beautiful, all right? You know, again, messed up, right? And so, but that's what they kind of used, okay? But all of that comes from, again, Pascal's triangle, all right? And so, all right, so that comes from Pascal's triangle. I left you instructions on Google Classroom to check out another website for some additional fun facts, which I think is really neat. So go ahead and take a look at it, and then we'll do our lesson on Friday.